Now we wanted to do the solution as a first order homogeneous equation. We can also do it as a separable equation. Our original equation was separable. Remember, our original equation was dq dt equals vs minus q over c divided by r. Well, first thing we want to do here is make this a simple fraction so it becomes easy to separate our variables. And we do that using a common denominator of c in the numerator, and then our c in the denominator goes into the denominator of the entire function, and certainly you understand the algebra of that manipulation. So that we then divide by the only term that involves q, which is this numerator, and we get dq over vsc minus q. And we don't really multiply by dt, but the operation acts as if we're multiplying by dt. And we get dt over rc. And we integrate both sides of this. And that's such a straightforward integral. I'm not going to go through those details. Certainly, you know how to do that integration. This is going to give you negative natural log of vsc minus q. And this is going to give you just t over rc plus a constant. Solving this then for vsc minus q, we would multiply both sides by the negative 1, giving us a negative t over rc here. And we'd multiply our constant by negative 1, but in multiplying an arbitrary constant by negative 1, we still get an arbitrary constant, so I'm not going to bother putting a negative on this constant in this step. Again, the constant is completely arbitrary, so it's not necessary to do that. We get vsc minus q then, using the fact that the natural log is an inverse function to the exponential, is e to the negative t over rc. It's actually e to the quantity negative t over rc plus a constant, but that is equal to e to the negative t over rc times e to the constant, just using the laws of exponents. So again, I'm not writing out every step, but that should be familiar to you. Then we can say that, well, that equals a e to the negative t over rc, where a is your e to the constant. So e to the constant becomes sort of an arbitrary constant a, except that a has to be greater than 0, because e to whatever this constant is, whether this constant is positive or negative, is a positive number. The exponential function gives you only positive results. So a has to be a positive number. Now we have our general solution. If we solve for q, and I see let's see, it's got a piece of chalk. When we solve for q, we actually get a minus here. We multiply through by a minus. We get negative a e to the negative t over rc, and then plus our vsc. So our solution for q would be this. And in this case then, our initial condition q of 0 equals 0. Q of 0, we're going to get a 1 from the e to the negative t over rc, because when t is 0, this is 1. And we get vsc minus a equals 0, so that a has to equal vsc. And I've got an equal sign here when I need an arrow. This implies that q is vsc times 1 minus e to the negative t over rc. And this solution agrees completely with the solution we got when we solved the equation as a linear non-homogeneous equation in q and t. In the next video, we'll look at the graph of this function, which is fairly simple and straightforward, and probably something you already know how to do, but let's take a look at it just to be sure.